Hello dear students. So, in continuation to our last lecture, we will talk few more aspects about the magnetosphere of Mars and then some aspects about the magnetosphere of the Earth. Okay. So, the magnetosphere of the Mars is an induced one. That means it has come into existence because of the interaction of the solar wind with the atmosphere of the planet. The Martian atmosphere diverts the solar wind because the Mars lacks a significant planetary magnetic field. Like the Earth, it cannot divert it. Mars is an induced obstacle. The ionosphere interacts with the solar wind, very unlike the Earth, which is encapsulated within the intrinsic magnetosphere. The magnetosphere buffers us from charged particles in the solar wind. So, that means the magnetosphere is just a cavity which is protecting the Earth from the shower of the solar wind particles. So, the induced magnetosphere of planets, Venus for example, the magnetic moment is less than 100,000th that of the Earth. So, because of the slow rotation, so remember this number 100,000ths. Okay. Plays no role in the solar wind interaction with the planet. Still, we do not know how much atmosphere is being lost to the solar wind. Mars, on the other hand, its precise size of magnetic field is not known, but its strength is much less than 1,000th of the Earth's magnetic field. Like Venus, the intrinsic magnetic field is not significant for the solar wind interaction. The ionosphere is thought to be magnetized because the solar wind dynamic pressure exceeds the thermal pressure of the ionosphere. Other features such as the bow shock and magnetotail are very similar to those of Venus. And for the case of comets, when comets come in contact with the solar wind, comets are much smaller objects than planets if only their nuclei are considered, not the coma. The size over which the cometary gas can spread in the solar wind is thus controlled by the speed of the expansion of the cometary gas, about 1 kilometers per second, and the ionization time, about a day at 1 astronomical unit from the sun. So, that was something about the induced magnetic field, right. Now, we talk about the intrinsic magnetospheres, intrinsic magnetic field by the virtue of the planetary core, which is having a lot of charged particles and also rotating at a reasonably high speed. So, geomagnetic field of many planets can be approximated to a dipole. So, it is basically a north-south bar magnet kind of an arrangement where you have two poles and they are separated by distance. The forcing by the solar wind modifies this field, creating a cavity called as the magnetosphere, right. So, the forcing, the solar wind forces this magnetosphere to adjust itself in this particular way. This is the way that magnetosphere of the planet Earth will look like. So, you have on one side you have the you have a compressed magnetic field lines. On the other hand, they are extending to a very large distances. So, you have the bow shock, which is in place because of the sudden decrease of the solar wind's velocity because it encounters an object, and then you have magnetopause is the top magnetosphere where the magnetosphere does not have, after which the magnetosphere does not have any influence. The current sheet is there to separate the opposite polarities. Magnetosphere shelters the surface from the high energy solar wind. The outer boundary of the magnetosphere is called as the magnetopause. In front of day side magnetopause, another boundary called the bow shock is formed because the solar wind is supersonic, right. So, region between the bow shock and the magnetopause is called as the magnetosheath. This region is called as the magnetosheath. Okay. So, what is the height of magnetopause? So, we have evaluated the height of the ionosphere based on the simple assumption of the pressure due to the solar wind becomes equal to the pressure due to the planetary atmosphere. We have evaluated the height of the ionosphere. And what is the height of magnetopause? Because here the magnetopause's depth is decided by the pressure balance between the solar wind and the magnetosphere. Now, here most interestingly, the height, I forgot to mention here, the height of the magnetosphere is compressed not by the dynamic pressure. Here the pressure is the magnetic pressure countering the exactly opposite, right. So, here we cannot talk that there is a magnetic line of force, and this magnetic line of force is experiencing because of the change of momentum. Here the pressure balance is because of the magnetic pressure, that is b square by 2 mu naught. In the earlier case, when we were talking about the solar wind's interaction with the ionosphere, there the pressure balance was the dynamic pressure. So, the height of ionosphere or the height of ionopause can be evaluated using the pressure balance of the dynamic pressure, and here it can be evaluated using the magnetic pressure, right. So, the magnetopause is located where the Earth's magnetic field's pressure balances the pressure due to the solar wind. So, the magnetic pressure is b square by 2 mu naught, magnetic pressure due to the Earth is b square by 2 mu naught. If the dipole moment of the Earth is capital M, the field along the equator varies as Be by r cube. So, Be is the field at the equator. So, it decays very fast. So, Pe is the pressure at the equator is b square by 2 mu naught r power 6. So, this becomes square. So, you have 6. So, we can therefore write the pressure due to the solar wind is half rho SW V SW square and half, yeah. So, you can write the pressure due to the solar wind becoming equal to the magnetic pressure. So, the height of the magnetopause varies as r approximately equal to pressure due to the solar wind taken to the power of minus 1 by 6. So, equating these two, the height of the magnetopause can be written as Be square by mu naught n m V S W square raised to the power of 1 by 6. Right. So, we can put the actual values and then we can calculate the value of r. Right. So, now we have established how different types of objects will interact with the solar wind. Like if we go back a couple of lectures or more than like 4 or 5 lectures before, we have made a statement. The aurora is the complex outcome of interaction of charged particles with the Earth's atmosphere in the presence of the Earth's magnetic field. It is a complex outcome of all these things put together. Now, when the planet has a magnetosphere, it will not allow the charged particles to directly penetrate into the atmosphere, or it will not allow the charged particles entry anywhere else apart from the polar regions, right. So, Jupiter has very strong magnetic field. So, you see Jupiter has very significant auroral emissions. So, these emissions are because of the charged particles being guided into the cusp region of the planet. So, this is the reason why we have aurora at the poles, right. Yeah, this is Saturn and this is the case of Jupiter. Now, we come to the basic topic, which is the solar wind acceleration processes. Solar wind, how the solar wind attains a tremendous amount of velocity. What happens for it to get this very high velocity is going to be the topic of discussion in this lecture. So, solar wind has one very important feature that we have to explain is how solar wind, one, how it escapes the gravity, number two, how solar wind reaches supersonic speeds, right. So, these two are the things. Why they are very difficult kind of phenomena to understand. How does solar wind escape the gravity? So, you can take the sun, its temperature at the surface is 6000 Kelvin. As we know, the temperature away from the sun does not decrease, rather increases for some reason, which is not totally understood. Now, if you take this value of temperature and if you calculate what will be the velocity of an electron at this temperature, and then you put this velocity in comparison with the escape velocity, you will be able to find out whether the gravity of sun is strong enough to hold this particle or not. And then you will realize, then you will appreciate the solar wind acceleration processes, right. Before we go there, so the Earth's atmosphere is stationary. The sun's atmosphere is not stable, but is blown out into space as the solar wind, filling the entire solar system, right. So, what I am trying to do is I am just trying to put some very basic features of solar wind. Then we will try to ask the right question, what is the physical mechanism which attributes these characteristic parameters to the solar wind. right. So, Earth's atmosphere is stationary, like I said. So, this is the solar wind is filling the entire solar system. The first direct measurements of the solar wind were in the year 1960s, but it had already been suggested in 1900s itself that there is something, there is a gas flow away from the sun. To explain the correlation between auroras and sunspots, Birkeland in 1908 suggested a continuous particle emission from the sunspots. Okay, why do we get to see auroras only during the time when there are a lot of when there are a lot of sunspots on the visible disk? So there must be something which is connected between these two things. Why there must be something coming out of these sunspots and depositing its energy in the polar regions. Others suggested that particles were emitted from the sun only during the flares and that otherwise space was empty. So the other explanation was the solar wind, like I said in the beginning, solar wind is a constant stream of particles escaping the suns. Several millions of tons of mass is escaping or being thrown out into the space. So this solar wind, so more importantly, this solar wind is what creates the boundary of the solar system. So this cavity, the entire cavity is basically, there again the balance is again the same. The pressure due to the interstellar space cannot override the pressure due to the solar wind. So that is where that cavity, the entire cavity is where the balance is intact. The edges of this cavity are where the balance is struck, and inside it the pressure due to the solar wind supersedes the interstellar pressure. What it means is that so some people thought that solar wind is not a constant thing, rather solar wind is in place whenever there are solar flares. Otherwise, the space is empty. Space was assumed to be empty. Now we know it's not empty. Solar wind is a constant flow, right? So observations of comet tails led to the suggestion of a continuous solar wind. So no matter whether there are solar flares or coronal mass ejections, comets always have tails, coma. So like I said, it is basically evaporation of the water, which follows, right? So the question of continuous solar wind was resolved in 1962 when the Mariner 2 spacecraft returned 3 months of continuous solar wind data while traveling to Venus. So this was the first observation which conclusively said that solar wind is a constant phenomenon. Solar wind is omnipresent in the entire solar system, constantly, always, right? So the cometary tails always point away from the sun. This is a more interesting. So whenever you see a comet, I mean comets are not generally seen every day. They come, few of them come after a few decades. Their trajectory is like they become visible after several decades, and that is periodic in nature, right? So regardless of the comet's direction of the velocity, whether it is moving towards the sun or whether it is moving in a perpendicular to the ecliptic, in any direction, the comet tail always points. So if this is sun, let me draw it. If this is sun, whether the comet is moving in this direction. So if the comet's velocity is in this direction, let me draw. So the comet tail is like this. Okay. So whether the comet is, again, the comet is moving like this in this picture, the comet tail is also like this. So this direction of the tail is basically, so the comet is moving into its tail. Whether this tail always points away from the sun. Why? Because the solar wind is pushing this tail in that particular direction. Solar wind forms the ion tail. Solar wind must have very high speeds relative to the comet to align the tail with the sun's direction. So the radiation pressure on micro-sized dust grains forms the diffuse dust tail. Grains have less sunward force, of course, move farther away from the sun, but fall behind the radial direction because their angular speed is lower than when it is closer in, right? So that is the reason that you see the comet tail away from the pointing away from the sun. So measured solar wind speeds, in this picture you see that. So these are the continuous measurements. They indicate solar wind speeds vary over a period of time, and this is a constant phenomenon. Now let us talk about the observations of solar wind. Let us put some numbers to perspective. So These are the observed properties of solar wind near the orbit of the earth, right. Near the orbit of the earth, you will see that there will always be 6.6 protons per unit volume, per cc, and there will be electrons, 7.1 electrons per cc, and there will be He2 plus, the ions. He2 plus ions will be 0.25 per centimeter cube. The flow speed is nearly radial, which is 450 kilometers per second. So, always remember this kilometers per second, not meters per second. Proton temperature is 10 to the power of 5 Kelvin, and electron temperature is 10 to the power of 5 Kelvin, 1.4. So, they are almost the same temperature, but their masses being different. We will try to attribute different velocities, but still they travel in unison. That means, the solar wind electrons being lighter will not really travel fast. The protons or the ions being heavier will not lag behind the electrons. This is because of the ambipolar diffusion. So, that is a different concept in plasma physics, but still. So, the magnetic field strength of the solar wind is nearly nanotesla, very small, and it is also useful to describe the solar wind in terms of quantities that are conserved in plasma flow. What do you mean conserved in plasma flow? As they flow, flux through, you take a sphere, you take at one astronomical unit, you take a sphere which is representing the earth. What will be the flux that goes through this sphere? Protons will be 10 to the power of 35 protons per second. So, that is a huge amount of mass that is flowing, that is escaping the sun. The mass is 1.6 10 to the power of 12 grams per second. Radial momentum is 7.3 10 to the power of 14 Newton. Kinetic energy is 1.7 10 to the power of 27 ergs per second. Thermal energy is 0.05 10 to the power of 27 ergs per second. The magnetic energy again is very high. The radial magnetic flux is 1.4 10 to the power of 15 Weber. So, we have seen the various statistics about the solar wind. What are the compositions in the number of particles, and what is the average velocity of solar wind, and what is the particle flux at a distance of 1 astronomical unit, and so on. Right. More importantly, solar wind is actually a natural plasma laboratory. What do I mean by that? It means that solar wind is a demonstration where various different types of plasma processes are actually being demonstrated successfully, right. So, one of the first greatest triumphs of the space age was the experimental proof of the existence of solar wind that fills the solar system. We have seen this cavity that surrounds the sun is basically filled by the solar wind, the radially outflowing solar wind in all directions. It goes to a point where the dynamic pressure exerted by the solar wind equals the pressure that is exerted by the interstellar plasma. Right. So, this cavity is mainly maintained by the solar wind. Now, the experimental demonstration of the existence of solar wind or the persistent flow of solar wind to maintain this cavity is considered the greatest triumphs of the space age. That means, this has led to a lot of discoveries as such, a lot of discoveries or a lot of understanding of plasma physics to begin with. Right. The solar wind serves as a magnificent natural laboratory for studying and obtaining understanding of processes and phenomena that occur in a variety of other space plasma, such as astrophysical plasma or things like that. That means, understanding of this has really given us a more detailed analysis of various different types of plasma, or to be more precise, solar wind plasma is considered as a natural laboratory where things are already in place. So, we try to understand this, we will have a lot of answers. Okay. So, the various space plasmas such as astrophysical plasma or many other types of plasma are came very handy in understanding the kinetic, fluid and MHD aspects of plasma, how the description of plasma can be complete only when you consider the plasma as a fluid and attribute electric and magnetic properties to this fluid, which is basically nothing but the MHD. And things like plasma heating and acceleration, collisionless shock physics, energetic particle production and transport, how the energetic particles are produced and how they are transported from one point to another point in the solar system. What kind of physical laws do these particles obey, and all these things. Understanding of all these various different aspects has been from the solar wind itself. So, the magnetic reconnection, the formation of magnetosphere, various physical processes and dynamical processes of magnetosphere, all these things came, the understanding of all these aspects was driven by the solar wind itself. That is why solar wind is considered as a natural laboratory of plasma physics. Okay. Or more importantly, evolution and dissipation of waves and turbulence in plasma. Right. So, the understanding of solar wind has led to so many different aspects of physics. This is the most important thing about solar wind plasma. Right. So, one very important aspect about the large scale fluctuations of solar wind, we have seen what are the parameters or what are the constituents of solar wind plasma and how large or how small is the concentration of these constituents such as protons, electrons, ions. We have seen all those statistical data. But most importantly, these numbers vary over a very large context. That means these numbers can be small and these numbers can be very large at some times. So, various other factors come into picture when we have to understand the variation of solar wind parameters. So, the solar wind speed, basically we consider the solar wind speed somewhere let us say 400 and 450 kilometers per second is what we can see in the proximity of the earth, or it can go to as high as 780 or 800 kilometers per second. So, like I said before, this is kilometers per second, not meters per second. Okay. So, this is something that you should remember always. So, the solar wind speed and the density have large variation on time scales of days. So, it can, the variation can of course be between the solar cycles, between maxima and minima, but the density and the wind speed can have large variation over the time scales of days itself. Of special interest are the high speed streams actually. These are more important phenomena. So, the flow speed varies from pre-stream levels, let us say 400 kilometers per second, reaching a maximum value of 600 to 700 kilometers per second in just about one day. Okay. And the density rises to high values of let us say 50 particles or electrons or protons per centimeter cube near the leading edges of the streams, and these high densities generally persist for about one day. Right. So, what triggers these large values of densities or large velocities is of a particular interest actually. So, the proton temperature varies like the flow speed itself. The high speed streams tend to have a dominant magnetic polarity. This is the most important aspect. Okay. The high speed streams tend to generally have a dominant magnetic polarity. Okay. So, the dominant source of high speed streams is thought to be field lines that are open to the interplanetary space. So, suns, there are few magnetic field lines which are open and which are closed. These open magnetic field lines are supposed to be the origin for the high speed streams, and these regions are generally called as the coronal holes. So, coronal holes, you will also hear about coronal holes when you are trying to understand the high temperature of corona and things like that. So, when I say variable, it can be between 400 to 700 kilometers per second. So, this is just a figure which shows how rapid the velocities of the solar wind can change from a highest point to the lowest point. Let us say that this is 310 or 320 kilometers per second, and the peak value is 550 kilometers per second, or it may go as high as 600 kilometers per second itself. So, these velocities are demonstrated by fast streams. Okay, now, if you see on the x axis, the variation is over few days actually, it is not more than like 10 or 15 days, that is it. So, within this short period of time, the solar wind velocity can go from a very low value of 300 kilometers per second to as high as 600 kilometers per second. So, along with the velocity or the speed, the density also changes drastically. So, that means the variability in the solar wind can be demonstrated within a few days itself. right. This is some observation which was made using the Solar Heliophysical Observatory, and it just proves how fast can the solar wind vary in terms of velocity, right. And what is it? This has mainly to deal with the fast solar wind streams. So, if you look at the statistics, it is the most probable, or the average velocity is of course not very fast. The faster velocities are generally, the incidences of faster velocities will be small, but the mean velocity, let us say the slow solar wind velocity, is the most likely thing that you will find on any given day. Right. So, now solar wind has something that is closely associated with itself. Like I said, solar wind is a plasma intercoupled with the magnetic field, which we call as the frozen in magnetic field. So, associated with the solar wind, we define what is called as the interplanetary magnetic field. Now, we must understand all of this thing, all of this discussion about the solar wind is only possible because of the differential rotation of the sun. Sun rotates around itself at different speeds at different latitudes. So, this complicates the inner magnetic field of the sun. The magnetic field lines are stretched at different velocities at different points, and as a result, over the period of 11 years, what happens is these magnetic field lines will cross each other and will emanate out of the photosphere, giving out a possibility for the magnetic reconnection to occur or plasma to flow out of these knots. Right. So, that is the basis. I think we have discussed that at some point of time, but so that is the origin of all this solar wind flow or whatever it is, right. So, associated with this solar wind flow, we define the interplanetary magnetic field. So, intermixed with the outflowing solar wind is a very weak magnetic field, which is called as the interplanetary magnetic field, or we generally call it as the IMF. So, you see, interplanetary magnetic field, that means the magnetic field which exists between the planets throughout the solar system, and the solar wind is the medium which takes this interplanetary magnetic field from one point to another point. So, on the average, the interplanetary magnetic field is in the ecliptic plane at the orbit of the Earth, although at times it can have substantial components perpendicular to the ecliptic. So, if you consider the sun to be this and the Earth to be this, so this is the ecliptic plane over which the Earth rotates around the sun, right, like this. So, the interplanetary magnetic field is in this particular plane, which I am not able to draw because of this limitation. So, now we are not looking in the from the perspective of, let us say, from the top, rather if this is the equator now, right. So, generally it is ecliptic at the orbit of the Earth, but it can have substantial components. So, what decides these things is actually part of the solar physics or magnetospheric physics, things like that, right. But on a more generally agreeable consensus, we can say that it is more often, it is along the ecliptic of the Earth and Sun system. The hot coronal plasma has extremely high electrical conductivity, and the interplanetary magnetic field becomes frozen in to the flow. So, solar wind is intermingled with this magnetic field. So, if the sun did not rotate, the resulting magnetic configuration would be very simple. Of course, like I said, it is only the differential rotation which is causing all of these things to exist to begin with, right. So, this is how the differential rotation stretches the magnetic field of the sun inside at the equator, because it is rotating fast. So, as a result, what happens is over a period of time, so this will very strong coupling between the magnetic field lines, and this is what results in the formation of sunspots or coronal mass ejections, all those things. Okay. So, so had this been the sun did not rotate, or had it been the case that sun is rotating uniformly across the latitudes, it would have been very simple, right. But we know that the sun rotates with a sidereal rotation period of 27 days. It rotates around itself in certain amount of time. Okay. So, as the sun rotates, the base of the field lines frozen into the plasma rotates westwards. Yeah, this is east to west, westwards, turning the radial field lines into an Archimedean spiral. So, if you take a packet of plasma which is being thrown out into the interplanetary space, and since the sun is rotating, this packet of plasma will not go out in a radially outward direction, rather it has a velocity component like this. So, if you see what is being drawn is the loci of succession of fluid parcels, 8 of them in this sketch, emitted at a constant speed from the source with a source fixed on the rotating sun. So, you can see it in both ways. So, if this is point 1, as time progresses, as the sun rotates around itself from east to west, so the packets will trace a path like this. So, this is the spiral locus of fluid parcels emitted from a fixed source. So, this is the source. So, as the sun is rotating, the source has now come here. While it came here, it was releasing plasma outside. So, the path will look something like this, right. So, if you go ahead, so we can assume a plasma parcel on the surface at a source longitude of phi, at a longitude of phi, and a source radius of r naught, right. So, at a time t, the parcel will be found at the position phi of t is equals to the angular velocity of the sun times the t, which is time, plus phi naught. And the distance of this parcel at an amount of time t is the velocity of the solar wind, because it is travelling outwards with this velocity v sw times t, r is equals to v t plus r naught, right. So, eliminating, so these two, you take 1 and you take 2, and eliminating time, if we get rid of time here, so that means we have to take r minus r naught by v w and then substitute this into this, you will get that r is equals to the velocity of solar wind times, what is this? This is longitude, and this is the source longitude, and this is the angular velocity of the sun plus r naught. So, this is how it looks like. So, most importantly, the magnetic field lines deduced from the isothermal MHD coronal expansion model for a dipole field at the base of the corona, this is how it looks like. So, the dashed field lines, the dashed lines that you see here are ideally for a dipolar magnetic field. So, you know what is a dipole magnetic field? So, just a north-south magnetic field, so like this. So, if it is an ideal dipole magnetic field, this is how it should look like. But the MHD modeling shows that the inner magnetic field lines are less than 2. The magnetic field lines which are closer to the sun near the equator are closed, and that at higher latitudes the field lines are drawn outwards and they do not close. So, these field lines are the ones which are not closed. So, if you take this to be the magnetic north and the magnetic south, so the field lines diverge from the magnetic north and converge at the magnetic south, right. So, what you see here is that the inner magnetic field lines are opening and closing, that means diverging and converging on the surface of the sun itself, but the magnetic field lines at the higher latitudes, they are not closed, they are open magnetic field lines. So, these field lines that do not close nearly meet at low latitudes, but do not reconnect. This abruptly changes in the magnetic field polarity is maintained by a thin region called as a high current density interplanetary current sheet. So, we think that since the polarity of the magnetic field is changing from 2 points which are either sides of the equator. So, what we think is that we assume that there is a current sheet which is separating these 2 poles or these 2 points of opposite magnetic polarity. So, this current sheet separates the plasma flow and field lines that originate from opposite ends of the dipole magnetic field. So, this current sheet is what separates the opposite magnetic field. Okay. So, the IMF at any given point of time can be directed either inwards or outwards with respect to the sun. Okay. That means, depending on where you are looking at, it can appear that the magnetic interplanetary magnetic field is appearing to be outwards from the sun, or if you are looking at a different point below the current sheet, for example, you will find it to be inwards the sun. So, one of the most remarkable observations from the early space exploration was that the magnetic field polarity was uniform over large angular regions, you see angular regions. So, this is, let us say if this is the sun from the top, these angular regions, what you see, it was assumed that the polarity was uniform over large angular regions. So, let us say all this region, throughout this region the polarity is 1, let us say it can be towards or it can be away, and with this, let us say with this the polarity is completely different in this angular region. So, the polarity pattern repeated over succeeding solar rotations. These regions of one polarity are called as the magnetic sectors. Wherever you have the same polarity for a very large period of, let us say, large angle, you call that a magnetic sector. Okay. So, in a stationary frame of reference, the sectors rotate with the sun. So, if you consider a stationary frame of reference, if you say that you are looking at the sun and sun is rotating around itself, you will see that the sectors are also rotating along with the sun. So, typically there are about 4 sectors like I have drawn here 1, 2, 3, 4. So, the sector structure gets very complicated during the solar maximum. Like I always say, solar maximum is when things are very complicated. There are a lot of sunspots, there are a lot of prominences, all those things reach their maximum values only at the solar maximum. Why? Solar maximum happens to be that period of time over which the magnetic field has been getting complicated and is at the height of its complicacy, and that is when the magnetic field is trying to shut it off, or it is just trying to get everything sorted out and go back to a simple magnetic field which looks like a dipole magnetic field. So, the sector structure gets very complicated during the solar maximum. So, one thing that we have understood is because of this open and closed magnetic field lines, the magnetic field lines appears to be converging or diverging from the sun at different points, at different areas. So, over a large angular region, the sector appears to be uniform, and there happens to be 4 such sectors for the sun. So, this is the sector structure inferred from IMP satellite observations. Plus signs are away from the sun and minus signs are towards the sun, you see. So, this is a sector, plus signs are away from the sun. So, this is the arrow is accurately drawn. So, this is away from the sun. So, where you see here, and minus is towards the sun, right. So, it depends where the planet Earth is, right. So, if the Earth is here, it will see something like this. If the Earth is here, it will see something opposite. So, entirely you have sector number 1, 2, 3 and 4. All right. So, the interplanetary medium or the region between the planets medium and the IMF, that is what we are actually trying to find out. So, it is intermixed with the streaming solar wind and it is a very weak magnetic field. Weak magnetic field, you have to speak in a relative context just to say that this is a weak magnetic field. Okay. But most importantly, the solar wind is a high beta plasma. Beta value, somewhere we have defined, beta value identifies the ratio between the pressure that can be exerted if you consider the solar wind plasma as a fluid and the pressure, the magnetic pressure B square by 2 mu naught. If you take a ratio of that, you will get what is called as the beta, and beta value signifies how intense is the magnetic field that is present in the solar wind plasma and how large a pressure that can be exerted by that. Okay. So, solar wind is considered as a high beta plasma. So, the IMF is frozen in, the IMF goes, the interplanetary magnetic field goes wherever the plasma goes. So, consequently, the spiral pattern formed by the particles from rotating sun, originating from the sun, is also manifested in the IMF. This is the most important thing. So, wherever you see IMF, you have a spiral pattern associated with it. The field winds up because of the rotation of the sun. That is, this you see, this sprinkling kind of motion of is because of the rotation of the sun. So, fields in low speed wind will be more wound up than fields in a high speed wind. This is a very important message that we should remember. So, the winding up of the fields around the sun are more for a low speed wind in comparison to the high speed wind. Okay. So, until 1990s, our knowledge of the heliosphere was limited to the ecliptic. So, we always use it to think that whatever happens in this plane is everything, Okay. The Ulysses spacecraft observed flow over both the northern and southern poles of the sun. Right. So, that means the solar wind flow can actually be from the polar regions as well. But what has been observed is that there is no latitudinal gradient in the magnetic field. You see the latitudinal gradient in the radial magnetic field BR. So, the magnetic flux is removed from the poles towards the equator regions 1, right. So, this sketch showing equatorial current sheet and the magnetic field lines, right. So, since the polarity is changing, a current sheet has to facilitate that change in the polarity, that is what I was talking about. More importantly, so there is a solar wind outflow from the higher latitudes as well, that is what was demonstrated by the Ulysses. So, the plasma measurements show a dramatic change in the velocity with the latitude in observations taken between 1992 and 1997. What do you see in this figure? You see that along the x-axis, along the y-axis you have the speed, of the solar wind. So, what you see is if you take this to be the sun, and this happens to be the latitude. So, you see higher latitudes, the velocity is going to very high values. So, the velocity increases from about 450 kilometers per second at the equator to about 750 kilometers per second above the poles. So, above 50 degrees latitude, only fast solar wind streaming out of coronal holes were observed. Yeah. So, up to 30 degrees a recurrent CIR was observed with a period of about 26 days. These are the observations. So, near the equator, the curvature force due to the magnetic field reduces the solar wind speed. So, you are more likely to find high speed solar wind from a high latitude rather than a low latitude. Right. So, this is the current sheet that we think is separating two oppositely directed magnetic fields. Now, if you see, this current sheet gets complicated as the solar cycle progresses, and it depends on the position of the earth on any given day where this current sheet is with respect to it, whether it is going to see an inward directed magnetic field or an outward directed magnetic field. Right. So, this is a wavy structure of the heliomagnetic current sheet due to the current sheet's inclination to the sun's rotational equator. Right. So, it depends where the earth's orbit intersects this current sheet determines whether earth sees a positive or a negative magnetic sector. Right. So, this is some information about the solar wind. Yeah. So, when it comes to the observation of solar winds, these days there are a lot of satellite based measurements to understand the variability of solar wind, how the solar wind is released, how fast it goes, it flows, and how does the compositional changes occur over a period of several years or several days or several cycles or whatever it is. So, if you look at the broad spectrum of the instruments that are available to us, you will see that most of these instruments are within the magnetospheres. That means they are not actually recording anything directly about the solar wind. So, they are more importantly studying the effects of the solar wind on the magnetosphere. But one very important instrument is this SOHO, which is observing the sun directly. These instruments are located at the first Lagrange point, where the gravitational pull due to the sun and earth equals itself. That means any object placed at that particular point will not experience any resultant force either towards the sun or the earth. These points are called as the parking orbits. So, anything that is placed at that particular position will remain there itself. So, they are called as the parking orbits. Okay. So, people have been specifically the space agencies have been able to park few spacecrafts for the continuous observation of the solar wind. So, it is very important, these missions are very important. One is SOHO and another is stereo A and B. There are two missions which look at different sides of the sun spontaneously, getting to understand how the sunspots move over a period of time and how the coronal mass ejection will develop over a period of time, all those things. And this is also a very important instrument, ACE, Advanced Compositional Explorer. So, these instruments are enhancing our understanding of the solar wind and various processes which are associated with it. And of course, we have to mention about this instrument, this Voyager 2, maybe at the time when this graphic was being drawn, it was still in the solar system, but now we know that it has crossed, it has the cavity of the solar wind, it is out into the open space. Right. So what we have learned is we have learnt the basic characteristics of the solar wind. Now we have to understand how does the solar wind accelerate, how is it able to escape the sun's gravitational pull and go into the interplanetary space. That will be the topic of discussion for the next couple of classes.